Hello everyone. Welcome to the visual physics tutorial at CVPR 2020. My name is Achuta Kadambi and I'm a faculty member at UCLA. I'm joined by some fantastic co-organizers, Bill Freeman, Katerina Fragadaki, Laura Waller, and Ayan Chakrabarti. The website for the tutorial is shown in the blue link. Please bookmark it because it will include details to the Zoom link as well as any slides or follow-up material. The title of this tutorial is Visual Physics, and really represents how physics has always been a part of computer vision. For example, when we try to estimate the shape of an object, we analyze the physics of how light would propagate from a light source to an observation camera. Shown on the right is an object tracking example. Very early methods of object tracking used to consider kinematics in their derivation. These are classical examples, and since then, the field has exploded. We've seen a large growth in physics-based vision methods, from classical techniques like photometric stereo, which are still active areas of research, to now even cameras that can see around corners. For example, the Best Paper Award at CVPR 2019 last year was awarded for a breakthrough that was able to leverage the wave physics of light to see objects around the corner. So check out this example. You have this coin, a quarter, that's hidden from a source. And by analyzing the subtleties of the physics of this problem, one can recover the 3D geometry of the quarter to micron scale accuracy, even though it's not in the line of sight. These are very exciting problems, and we see dozens of papers on this at CVPR each year. Now, what's really interesting and what's perhaps timely for this tutorial is that in parallel, there's been increasing interest in leveraging physics, not just in computer vision, but also in the machine learning community. Here's one grand question. Just as Isaac Newton observed an apple falling and was able to discover the equations for gravity, could a machine do the same thing? What if a computer with a vision camera was sitting right where Newton was sitting? Could that computer estimate, learn the equations for gravity, gm1m2 over r squared? Here's an example at UCLA along these lines. One of our students is shooting hoops. We collect a bunch of videos of the student shooting hoops and feed that into an AI engine that is able to process these videos, these heterogeneous videos, into a discovered symbolic equation that matches that of the kinematic equations that describe motion. One can sort of apply this analysis to many different portions of the high school physics textbook. For example, you might have rotational dynamics. Here you have an object that is fixed to a stick that is rotated by a motor, and a visual physics AI engine is able to output the discovered law, the discovered physical law for motion, which is sinusoidal in nature. The success of these techniques really draws from the success of computer vision. The method that we introduced works by leveraging computer vision techniques like position detectors, which have been become very accurate in recent years. These positions can then be used to find embedding trends, which can later be converted into symbolic equations. Here's how the embedded trends could look on an example. On the left, we have some training data and testing data. Of course, these are very similar scenes. These are just scenes of video collection of the same, different group of students in a similar background tossing a basketball. Now, what's interesting is that in the embedding trends, variables with high correlation can be factored into a symbolic expression, and variables with low correlation are ignored. It's kind of an Occam's razor approach. And what this enables is it enables discovery of structured physical laws that we can use to rederive that equation. Now, shown here, I've displayed some video data where the training and testing is pretty similar, so one might be concerned of overfitting. But in the paper, which will be available on the last slide, the students have shown that you can actually train on synthetic data. As long as the physical laws match, you can train on synthetic data and test on real data. This may lead to more robust approaches in the future that can not just recover the high school physics textbook, but may also be able to discover more complex expressions for physics-based vision and imaging problems. Let me end by crediting our students for this work and their paper, which can be found on arXiv. In the visual physics workshop, we will have interactive live panels where we'll discuss topics like this. I hope you enjoyed the fast forward, and I look forward to seeing you on Zoom. Thank you.